Assalamu alaikum. How are you?
Assalamu alaikum, sir.
Walaikum assalam. Okay, so how many of you didn't start homework yet? Is there anybody who did not start homework 2 yet? So hopefully you all started, right? Okay, anybody has any question or confusion about the homework? Okay, so I think all the questions given in homework 2, we have solved similar question in the class. So I think you can relate all the questions with the classwork. But please, those who are slow to start, please start as early as possible. And your syllabus in homework 2 is almost the syllabus for our class test number 5. Okay. So class test number 5 will be held on next class, Saturday, 25th September. And the syllabus will be chapter 4 and 5. Basically, it's 3 sections, 4.1, 4.3, and the algorithms, linked state and distance vector 5.2. Okay, so anybody has any question about the previous class where we have solved distance vector algorithm? And we have also discussed about how hierarchical routing helps in internet, that is intra-autonomous system routing, and then in inter-autonomous system routing. We have learned the concept of autonomous systems. Okay, so any question on the previous class?
স্যার আমাদের কি অনলাইন কুইজ 5 অনলাইনে হবে?
Yes, online. It will be also online. So the similar type of questions, I think you already know about the type of the questions. Similar type of questions will be there. Okay, no question. So we will cover, I think, one particular topic today. Very interesting topic. It should be interesting to you. I think many of you have heard about the IP version 6. We will talk a little bit about the IP version 6. That is actually from chapter 4, the same section where IP version 4 addressing was there. And then after that, we'll start chapter 6, that is the data link layer. This is the last chapter for our final exam syllabus. So this is the overview what we will cover today. Okay, then let us start with IP version 6. So anybody has any idea about IP version 6? Any kind of idea? Anybody? What is IP version 6? Shafiq, any idea?
Sir, 128-bit IP address.
128-bit, right? That is one fundamental property of IP version 6. Right, Shafiq? Actually, I think many of us has some idea about IP version 6. It's a 128-bit. So,
Sir,
we have, yes.
Sir, I heard, sir, it's every single IP is public IP in IPv6.
Yes. In one sense, you are correct. Actually, there are different type of IPs used in IP version 6. It can be like used in a local network, and it can be used as a public, what we call public IP. That is actually has a different name in IP version 6, but the idea is correct, because to be able to use private IP in IP version 4, if we want to connect to the internet, we need NAT, right? Network address transfer, we need NAT. So in that sense, the idea of private IP is ad hoc in IP version 4. Actually, in IP version 4, before NAT, there was only public IP available. When they saw that, okay, public IPs will be exhausting soon, so we need to have some mechanism so that the exhaustion rate of public IP will be slow. So they introduced public private IP concept in every class, and then private IP cannot be routed in internet, so they have that mechanism of network address translation. So all these things in IP version 4 actually was a solution for a problem that creates another problem. So that is the history of IP version 4. In case of IP version 6, that is not the case, because already they saw what are the problems with IP version 4, so they have incorporated the solutions in IP version 6. So far, the development of IP version 6 was keeping those in mind. But we don't know what will happen in tomorrow, what will happen 20 years after, because when IP version 4 was first introduced in, I think, 60s, in that time, it was never thought about the growth of the internet, right? And then after few years, there was no class at first. There was no class. Then class ABC was introduced. Then there was all were public IP. There was no concept of private IP. Then private IP introduced. Then NAT introduced. So if you go through the history of IP version 4, lots of solutions were actually ad hoc, temporary solution. So that's why in 90s, late 90s, they have actually started to build IP version 6. The primary goal is definitely was to get more addresses. Like IP version 4 has 32 bits, IP version 6 has 128. That's huge, but there are many other things also. Okay, let us get some basic. Again, IP version 6 is a vast topic. So in this course, we can have only a basic understanding of IP version 6. I think that will definitely help you to understand better later on if you need somewhere in your career or somewhere in other courses. But we will not cover the implementation issues and very much details in this course. But as you know, we have in our university, we have Cisco Academy, where we have run the professional course. I think some of you already enrolled, some of you can think about this, where you will get more in-depth practical knowledge on networking. More on IP version 6. You will be able to configure IP version 6 also. Okay, but in this course, our target is to get some basic ideas so that at least we know the basic concepts of IP version 6. The IP version 6 actually comes to understand why IP version or the motivation of IP version 6. You have to know what are the main limitations of IP version 4. So this slide actually lists 3 major limitations. First one is definitely obvious: IP version 4 address depletion. So we have basically run out of IP version 4 addressing. We will see the status of IP version 4 currently. Actually, there is no more new block being assigned now, but the previously assigned blocks may have some holes there. So some of the IP addresses may be free, they can be reused, but no new blocks are not assigned. So IP version 4 address space was being exhausted from the last, I think, 20 years. So predicting that, they have started to think about IP version 6. As I said, it was more than 20 years back when they started to think about IP version 6. It's, I think, late 90s, 98 or 96, like that time. Lack of end-to-end connectivity. Another important thing in IP version 4 with the introduction of network address translation. Remember in chapter 1, we have solved one problem with IP address, then a MAC address, then port number. Exercise 12, If you can remember, in that case, uh, in that particular solution, I have told you that IP address will never change, source IP and destination IP will never change between the nodes, between the end systems, right? And at that time, I said there can be exceptions, and the exception is actually NAT. We have already read this in chapter 4, network address translation, the exception. Why it is exception? Because now it's no more end-to-end connectivity. The source IP and destination IP actually can be changed in the middle by a router configured with NAT. Is it correct? So when you use NAT, the intermediate router actually changes the source IP or destination IP. Is it right? Yes or no? We
Yes,
already
sir.
know NAT, right? We already know the mechanism of NAT. So what was one of the criticism, one of the drawbacks of NAT? I think it is listed in that in your textbook, that it violates the end-to-end argument, end-to-end connectivity. What is that? Normally, when a host communicates with another host, that host source has a source IP, destination have a destination IP. Normally, that source IP and destination IP in the packet will not change, right? During the traveling, but NAT violates that. That was the concept. It converts the private IP to public IP, and then again when returns public IP to private IP. So the IPs are changed in the middle. So what NAT introduced is a lack of end-to-end connectivity. That means no more, if NAT is used, no more one host can know directly the other host, because that may be inside the NAT. And this ended the direct communication with public addressing. What is the problem? The problem is actually private IP, but the consequence is now two hosts may not see each other, may not communicate directly if there is a NAT in the middle. The third point, increase network complexity. So this NAT, network address translation, creates a lot more complexity, right? Suppose you want to you want to develop an instant messaging software, right? You want to write a code. It is a peer-to-peer code, so the code will run in your machine. The code will run in a server. Now, normally in a instant messaging software, what we do? We normally send message directly to the friend, right? But your friend's machine may be behind the net. So is it possible to send a message from your machine directly to a friend's machine? What do you think? Did you get my question? Did you understand the scenario, what I am talking about? Your friend and you are exchanging messages, but your friend might be behind net, you might be behind net, right? So behind net means what? The host has a private IP or public IP? Tell me.
Private, sir.
Private IP.
Private.
Private IP. What we said, whenever we send something from a private IP or to a private IP, internet will block, internet will reject. Then how can you write a program so that one private IP can communicate with another private IP? Actually, NAT creates a complexity, so it's not directly possible. Not. You cannot ping. If you implement NAT in the, I think you have implemented NAT in the network lab, right? Did you try to ping a private IP? Did you try? Anybody? From the internet, from a server? You have implemented NAT in the lab, right? Network lab.
Yes, sir.
Yes. So in that case, did you try to ping a private IP inside NAT from the internet, from the ISP, from the outside? Did you try one time? Anybody? No? Okay, no problem. You did not. But if you try to ping a private IP, even if the routing is 100% correct, your NAT configuration is 100% correct. If you try to ping a local PC, a private IP from outside, it will fail. Why? Because there is no direct connectivity possible from internet to a private IP. Again, that is one inherent advantage of NAT. That is about the security. So no one from the internet can directly access my private network. That is one kind of security. But in other sense, it will not be possible. If you try, you will see that. But sometimes we need that. Why? Again, think about the instant messaging software. Think about Skype. Think about WhatsApp. Think about those softwares where basically the end users communicate, they exchange messages. How those softwares work then? So that is a question. The solution is a little bit complex, but what we have to understand here, NAT was meant as temporary solution and creates issues on network as a side effect of manipulating the network header's address. One other thing I think you can recall, if I say the netted router uses a port number, right? Is it correct? The router that configures NAT, whenever it translates in the NAT table, it creates a port number, right? Is
Yes,
it
sir.
yes or no? Yes. But port number is used by which layer? Which layer uses source port and destination port? Tell me. See, we are at the end of the trimester, so this type of questions should have a first answer, rapid answer from you. Should have. Which layer uses port number? Source port
The
and destination.
transport layer.
Very good. Transport layer. Which layer implements NAT? Which layer implements NAT? Network address translation. Network layer.
Network layer.
Definitely, we are at the network layer, chapter 4. So network layer implements NAT, right? So network layer, why network layer then uses port number? Do you get my question? That is one criticism of NAT. It works in network layer, so it should not use port number. That is a violation against the layering rules. Okay. So that is another thing. And network address translation causes latency. Latency means delay, and the troubleshooting issues. And most of the problems nowadays in IP version 4 are due to NAT. Keep in mind. And there is no NAT, no need of NAT in IP version 6. So these are the three major limitations in IP version 4 that has been dealt in IP version 6. Okay. So the first motivation was definitely the address space. 32-bit IP version 4 address space would be completely allocated, exhausted. So we need a larger address space. How much larger? 32 to 128. If you count this possible 2 to the power 32, you can write down. 2 to the power 228, you can also write down, but that's a very huge space. And it has been said that every leaf of every tree on earth will get an IP address like this. So it's a huge. But again, there are technologies like Internet of Things. There are newer technologies, billions of devices coming into the network. So we don't know how far it will be more than enough. Also, beyond the basic motivation, beyond the basic issue of address space, it has some additional motivations like to speed up processing or forwarding more and more faster. For example, in IP version 6, the header length is 40 bytes, okay? Fixed. You know, in IP version 4, header length is how much? How many bytes?
Sir,
20 bytes minimum, but it has optional. So if you have optional fields, you have to process those optional fields. You are not sure how many bytes must be the header, right? So it creates some extra processing. In IP version 6, fixed 40 bytes header. So no extra processing. That means processing will be faster. Forwarding will be faster. And also it enables different network layer treatment of flows. Flows means there are different type of packets flowing through the network, right? At the application layer, we can identify this is wave, this is FTP, this is SMTP, this is video streaming. We can specify. But at the network layer, we see only packets. So in IP version 6, there is a concept of flow level, we'll see in the header, that can differentiate among the flow of packets. So if suppose these are video packets, these are more priority packets, these are this type of packets, so this can be separated or given priority. So this is another issue. Okay. And now you can see why we need IP version 6. I have already mentioned. You can see worldwide there are different organizations. Did you hear about ethnic before? Anybody? Asia Pacific, right? Ethnic.
yes,
So
sir.
it's
So
for
IP address.
right, IP address allocation. Very good, very good. IP address allocation. So every part of the world has different agent of assigning IP address. They all work under a common central authority, but they assign IP address in different parts. So you can see Australia, Africa, Europe, then South America, North America. The IP addresses are being exhausted, and the possible exhaustion date is given here. In South America, it's 2011. So they are the first using up all the public IP space. Okay. Then North America or in they have June 2015, Europe 2012, Asia Pacific 2014. This is the estimated days that the IP version public IP addresses are exhausted. Even if there are some blocks remaining, there are some holes, as I said, but there are no newer, larger blocks are being assigned. In Africa, it's 2020. So maybe there are still some space there because Africa is not that developed in terms of internet and communication. So that's why they have estimated that is 2020. It's already past. Okay. So you can understand why we need IP version 6. The first thing, we need a larger address space, and in IP version 6, the address space is 128 bit. So you can create 2 to the power 128. So 2 to the power 32 to 2 to the power 128. You can assume how many times larger the IP version 6 address is compared to IP version 4. The development of IP version 6 also included fixes for IP version 4 limitations. So already we've seen some limitations we have mentioned in the previous slide. IP version 6 not only addresses space, it has also considered all those limitations and then enhancements. And as you know, issues with NAT, we have mentioned NAT is problematic. And also IoT, Internet of Things, huge number of devices will be internet. So we have to transition to IP version 6. But it's not a measurement like tomorrow or like the next month or like in 2023 we will move to IP version 6. It's not like that. We don't know how much time it will be needed to completely move to IP version 6. Okay. There are lots of IP version 4 traffic now still there. Billions of investments are there. So it will not be like overnight. It will take some time. But the percentage of transition to IP version 6 is continuously growing. Okay. Now let us see the IP version 6 header first, packet header. And if you compare with IP version 4, there are similarity is there. I think there are some problems with 32 bits. It will be 128 bit. There is a mistake there. It will be 128 bit. So some fields of IP version 4 is not here. For example, the fragmentation reassembly. Why this is not here, I will explain. But you can see more specific and less number of headers here. Destination source same as IP version 4, but in this case 128 bits. And there is a flow level, as I said. So the flow of different flow of packets can be identified or can be used to prioritize some of the flow of the data using a field. There is a priority field also. Identify the priority among the flow of datagrams. For example, we will give priority to video streaming, then the priority of web browsing. Okay. And then payload, you can see payload. So payload here is same as IP version 4. The payload will be the data from the transport layer or the application layer data. Now, what are the fields? Those are missing here, or those are removed from the header compared to IP version 4. First one, no checksum. No checksum. So checksum was used for what? For error checking, right? So now there is no error checking. Why? That is, in one sense, that is disadvantage. There is no error checking. Actually, this has been implemented so that it will speed up the processing at routers. One thing during the start of chapter 4, I think we have mentioned that the network layer, whatever mechanism you put in the network layer must be executed in every router. So if there are 10 routers, the process will be 10 times. If there are 100 routers, the process will be 100 times. So if you can remove some of the processing burden from the network layer, definitely the overall delay will be much less. So since transport layer use checksum, error checking, since data link layer does also error checking, so what they thought, okay, in network layer I can remove the error checking. If there is an error, it will discard, no problem. But if there is no error, then it will forward, and then it will be much faster. That was the reason why checksum was removed from IP version 4 to IP version 6. No fragmentation and reassembly. Again, fragmentation, extra processing, right? Reassembly, extra processing. So those processing burden is removed. Now what will happen if a router sees that, okay, the link is not supporting my packet size, there is no option for fragmentation, the router will simply discard the packet. Now you will ask me the question, okay, if that is discarded, then how can that packet reach the destination? Actually, in IP version 6, there is no fragmentation reassembly concept, but there are possible mechanisms where, okay, first of all, these packet size concept or all these complexities are put to the shoulder of end systems. So only end systems will decide. Router has no responsibility. That's why. Now the end systems will know, okay, what is the, it is possible to know out of 10 links, what are the what is the minimum MTU, right? It is possible to know. If the end system knows, the source knows, okay, that up to the destination out of the links, the minimum MTU is this, then the source will know what will be the maximum size of a packet. So fragmentation reassembly is not needed. You got the idea? So that is another point. And lastly, there is no options. There is no optional field. So fixed header, no confusion. So processing will be much faster. But there is an option to increase the header size, to extend the header size. That is through the next header. You can see here a next header field. Normally, next header field indicates the upper layer protocol, next header protocol. For example, TCP UDP, but it can be also used as to extend the header to some bytes from the payload. So in that case, next header will be used, for example, 20. If that is 20, then 20 bytes header will be added with the 40. Okay. These are the description of the fields. I think I have also already mentioned. Now, IP version 6 addressing format. So you know it's 128-bit. Now think about subnetting. Subnetting is also there. So IP version 4 addresses subnetting. If you subnet an address for class C, it's simple. If you do subnetting for class B, little bit more calculation, right? If you do it for class A, there is a, like with more number of bits, the calculation will be much more time consuming. Is it correct? So think about 128 bits. What will happen? If I ask you to do subnetting for 128 bits instead of 32 bits, what will happen? Is it feasible?
অনেক টাইম লাগবে।
Yes. Sometimes it is not feasible for human to do. So that is another issue they have done in IP version 6. Actually, we will not have time to go through that much details, but there are mechanisms where subnetting is much easier in IP version 6. Subnetting is much easier. Sometimes it is automated. Sometimes it's much easier. You don't need to do that bit by bit calculation. Anyway, what is the format now? 128 bits is the huge. Normally IP version 6 is written in decimal. IP version 6 is written in hexadecimal. Even if you write in hexadecimal, you can see the two examples on the bottom. These are hexadecimal digits. That means each hexadecimal digit is 4 bits. Still, it's a large one, right? So each part of here specified part, see the preferred format is there are 1, 2, 3, 4, 5, 6, 7, 8. 8 parts, each separated by a colon. Okay, and each part consists of 4 hexadecimal digits. 4 hexadecimal digits means how many bits? 16, right? So each of this part is 16 bits represented as hexadecimal. And if you count 1, 2, 3, 4, 5, 6, 7, 8, then 8 into 16 is actually 128 bits. But using hexadecimal, still it's a large one. So there are two very simple rules that can be applied to make a shorthand, to create a shorthand of a IP version 6 address. The first rule is omit leading 0. So you can only omit leading 0. You cannot omit the trailing 0. For example, 0, 1, AB, you can write it 1AB. 0, 9, F0, you can write it 9F0. 0, A, 0, 0, you can write it A, 0, 0. Trailing zeros you cannot omit. You cannot write it 0A. You cannot omit these trailing 2 zeros to write 0A. You can only omit leading zeros. Okay, so you have to write A00. 00AB, you can write AB. Is it clear? So first rule, simple. Remove all leading zeros. So in this example, see the entire address, and then when you write with no leading, no leading zero, that means removing leading zero, then it will be a little bit shorter. You can see 0 db8, so it is db8. 0 0 0 0, only 1 0, last 0. Then for each of these 0 consecutive zeros, write 1 0. But you cannot omit this colon. Remember, you cannot. So 0 2 0 0, you can write 2 0 0. Clear? Any question up to this point? Anybody? So applying this simple rule, we somehow minimize the representation, but still it's large, right? So apply the second rule. So second rule is a double colon can replace any single or contiguous string of one or more 16-bit hex states consisting of all zeros. Hex state means now there are 16 bits. That is called hex state. In case of IP version 4, we called octet. Can you remember? Because there were 8 bits, right, in each part, and separated by dot. Now it is separated by colon, and in each part there are 16 bits. So it's called hex state. If there are consecutive hex states, you can replace this with a double colon. For example, the same IP version 6 address, you can minimize it by removing leading zeros and also replacing these 3 consecutive zeros using a double colon. Is it clear?
স্যার ডাবল কোলন কি টু কনসিকিউটিভ জিরোর জন্য হতো না নাকি তিনটার জন্য?
Any consecutive zero. What is the minimum value? Anyone? What is the minimum representation of IP version 6 address? Minimum. If I say, how can I represent? What is an example of a minimum IP version 4 representation? Can I say double colon? That means if 128 bits all are zeros, how I can represent that? All 128 bits are zeros. Then how can you represent that? Can you represent that with double colon? Yes, you can. Because double colon says any single or contiguous. That means no non-zero value in the middle. If there is no non-zero value in the middle, you can represent the entire string of zeros as a single double colon. Clear? So in this example, you can see there are 2 set of zeros. One is the third hex state where there are 4 zeros, and one is the 5th, 6th, and 7th hex states where there are consecutive 3 zeros, right? 3 hex states of zeros. Definitely logical is to use the more number of zeros. So we have represented double colon for the 3 consecutive zeros, not for single zero. You could use for the single zero, no problem. But in this case, you have to use 0, 0, 0 in the third part. Because the double colon you can use only once. You cannot use more than once. Then there will be problem. Because the logic is very simple. In this case, how many zeros? Suppose you have given second one. How many zeros are there? How you can calculate? Simple. 2001, that is 16 bit. DB8 16 bit. 32. Third 0 16 bit. 48. Then 1111 64. Then 200 16 more bit 80. So if I subtract 80 from 120, can I get how many zeros in the double column?
Yes, sir.
Yes. So that is the simple logic. If you use more than one place, it's not possible. How many zeros in which part, right? So that's why for the second rule, you have to remember you can use only once the double colon. So definitely the logic is to use double colon for the largest part of zeros. Clear, everybody? Any question? So this is how IP version 6 addresses is represented and can be written in a shorter possible way. One other interesting thing I can tell you. What is the loopback address in IP version 4? What is the loopback address in IP version 4? Anyone? You have used many times in the lab. Ping. Anyone? No answer? Why 127 is used?
127.
Right. 127. Which class 127 belongs? Class A, class B, or class C? See, we are at the
Class A.
end of the trimester. Yes, class A. We are at the end of the trimester. So this type of questions answers should be rapid. Yes, Aziz, very good. Class A. So we should be very comfortable now with this addressing, with this theory, at least the basic concept. Okay, so class A. So class A, we know 24 bits for host, right? But how many address, how many single IP we need for loopback? Only one. So we need only one IP, whereas in IP version 4, an entire class A address is reserved for that. That means 2 to the power 24 minus 2 addresses possible, whereas we need only one address. Why that happened? Because loopback came before class, before private IP, before NAT. So when they started, they have decided, okay, 127 will be reserved for loopback because we don't need that much of addresses, right? It was the start of IP version 4. So since for backward compatibility, that was never changed. So although for loopback we need one address, in IP version 4 we have allocated an entire class an address space similar to Google, Microsoft, only for a loopback, right? Very interesting, but that is the case. That is the reality, and we cannot use 127 block for any other purpose, even if only one address needed, all other addresses blocked. Anyway, in IP version 6, there are huge addresses, 2 to the power 128. But do you know how many addresses reserved for loopback? One. Only one. What is their address? All 0, 1. All 0, 127 zeros, then 1. That is reserved for loopback. That is only one address we need and one address is reserved.
তাহলে কি
How-
ডাবল কোলন 1 লিখবো?
Right, very good, Mushfiq. Double quote 1. Because 127 zeros and the last there will be 1. So see, this is one simple example of efficiency of IP version 6. So you can write that loopback address using double colon 1. Very shortcut. Anyway, let us move. Now, as I said, at what time, when we should move to IP version 6? It's not like that. After a certain date, suddenly it will be all IP version. It's not like it's by phase. It's continuously moving to IP version 6, but we don't know how many more years we have to live with IP version 4. In your home network, you're using IP version 4. In your home network, you're also using, you can use IP version 6 for some cases. For example, in Bangladesh, I know some of the organizations have also moved to IP version 6, but they have to also keep the IP version 4 option also, because most of their customers are using IP version 4 and some using IP version 6. For example, Prothomalo and some other well-known popular websites, they have also IP version 6 capability. But it's not about implementing IP version 6. It's about how we can support all customers, all users. And still, most of the customers are from IP version 4. Okay. Now, that means what? That means you cannot completely move to IP version 6. You cannot implement IP version 6 network and expect everyone is using my server, my website, because I am using IP version 6. No. If you don't have the option for IP version 4, you will lose most of your customers, because you have to also support that. So that is called IP version 4 and IP version 6 coexistence. And there are 3 mechanisms. One is called dual stack. Basically, the router that needs to communicate between IP version 4 and IP version 6 must have a dual stack capability. Dual stack means like dual citizenship, like dual passport. Like it must support IP version 4, at the same time it must support IP version 6. And then there are, yes, question?
Yes, sir. ডুয়াল স্ট্যাক থাকার তো অ্যাকচুয়ালি ক্যাপাবিলিটি থাকতে হবে, রাইট? মানে সফটওয়্যার কেটে সাপোর্ট করবে।
Definitely. If you buy a router from a market, you cannot say it's dual stack. You have to ask for dual stack capability. You have to check whether it is dual stack capable. Then you can use that router in somewhere where you need to translate between IP version 4 and IP version 6. Okay, now If you understand the following two options, then it will be much more easier. One is tunneling, one is translation. That are another two coexistence mechanism. Tunneling means you have IP version 6 networks, but you have the IP version 4 interface in the middle. For example, ISPs are IP version 4, or your end systems are IP version 6. The network in the middle is IP version 4. In that case, you have to use tunneling. Tunneling means create a tunnel of create a IP version 4 tunnel between IP version 6 endpoints. So what will happen? There will be definitely a dual stack router in both at both end, and when it receives an IP version 6 packet, it knows that the intermediate node will not support IP version 6, so it will not convert, it will just put that IP version 6 packet inside an IP version 4 packet, and that will be carried away by the intermediate routers. And when in the other side there is a dual stack router, it will convert, it will extract the IP version 6 packet and then hand over to the IP version 6 node. So that is tunneling. Translation is like communicating from IP version 4 to IP version 6. See, in case of tunneling, IP version 6 is communicating with IP version 6, or IP version 4 is communicating with IP version 4. But in case of translation, one side is IP version 4, one side is IP version 6. Again, dual stack router is needed, and then it will convert IP version 4 data to IP version 6, and then when response, IP version 6 to IP version 4. This is called network address translation 6.4, NAT 6.4, but this is not the NAT of IP version 4. This is a different, this translates IP version 4 to 6, 6 to 4. Clear? Got the idea? Each one has a in-depth, but we'll see a just tunneling example. We'll not go through any other details. Any question, anybody, before I move? Okay, let us see a tunneling example. As I said, a tunneling is like this. So IP version 6 packet must be moved through IP version 4 network. So what the router will do, it will put the IP version 6 datagram inside the IP version 4 datagram, and then IP version 4 datagram has its own header, and IP version 6 datagram has its own header. But then IP version 4 will actually move. For example, when we say Ethernet connecting two IP version 6 routers, then it will be like this. Okay, so all IP version 6, no problem. But when we say it IP version 6, when we say IP version 4 network connecting two IP version 6 networks, then you can see like this. In the middle layer, all IP version 4 routers, these routers, these red routers cannot process IP version 6. So what you see here, A and F, they are completely IP version 6. Intermediate routers in the red zone in the middle, complete IP version 4. And B and E, they work as the broker, as the middle. They are dual stack. So they take IP version 6 data, convert to IP version 4, and then IP version 4 data, convert to IP version 6. Clear? So this is the idea of tunneling. Why it is called tunneling? Because it's like this. It's logically a tunnel between B and E, but there are many intermediate routers in the middle. Those are all IP version 4. Okay, like this, and they all encapsulate the IP version 6 datagram in IP version 4 datagram. So logically, it's a tunnel between B and E, but physically there are many routers in the middle, but they can only work with IP version 4. So B and E can tackle those. Clear the tunneling idea? We are not doing the implementation, so it's just a concept. And there is an example, clear example on how this is being done, but I'm not going through that much detail. Just if we understand the tunneling concept, that's fine. Any question, anybody? Okay, and IP version 6 adoption, I think I have mentioned already. There are very less. Google in USA is actually frontier in that case. They have technologically advanced, but still you can see Google says 30% of clients access services by application 6. I don't know, in our country, maybe 3%, 4% capability. And there is another organization, National Institute of Science and Standards and Technology. So they actually create reports based on the status. They said 1/3 of all US government domains are IPv6 capable. So it's still 2/3 not capable. It's still 70% of the Google clients, they communicate with IPv4. So see, that is one of the things. There is a graph here. Okay. And long time for deployment, we don't know. As I said, how many more years we need to coexist, or we need to be with IPv6 also. 25 years, it's already 25 years. I think 25 years counting from 1996. Actually, I said around 2000. Actually, it started, IPv6 started 1996, so 25 years. Think of application level changes in last 25 years, World Wide Web, social media, streaming media, gaming, teleconference. But why? There are reasons. I think some of the reasons I have mentioned, that because there are investments of billion dollars, so it is not possible to overnight remove those IPv4 networks and then put IPv6. So it will take some time. Okay. I think that is end of the concept, IPv6. Any question? Then I will move to our last chapter, that
Sir,
is,
আমি
yes.
আমি শুনছিলাম যে স্যার জাপান IPv6 কে এখন সবাই মানে মোস্টলি ইউজ করে, IPv4 এখন ইউজ করে না।
I'm not sure. I'm not sure because that is, IPv6 is encouraged, and if an advanced country can actually implement, like organizations can implement IPv6, but the problem is if there are IPv4 customers, then you have to also accommodate those. I'm not sure, but maybe they're in a growth rate, but I'm not sure whether they're 100% IPv6 already done. I'm not sure. Okay. Okay, so okay, that is actually part of the 4. It was part of the 4, chapter 4. Now let us start the last chapter in our syllabus, that is data link layer. So we have completed application layer, transport layer, network layer, and now we are at the data link layer. And in this course we will not have time to go to physical layer, but I think some other courses, for example, digital communication, communication theory, or optical communication. If you have those type of courses, you might have some physical media, physical layer issues there. And also mobile cellular communication, because every different network has a different physical media and corresponding data link. But we'll cover the general concepts of data link layer, and in this slide I have also mentioned the subsections we will cover. So possibly in section 6.1 there is a 6.1.1 and 6.1.2. There are 2 subsections, but we will cover only 6.1.1. Then 6.3, and then 6.4 we will cover only 6.4.1, that is ARP, address resolution protocol, very important protocol in networking. And then 6.4.3, that is probably switch table, how switches actually maintain their forwarding table or switch table. Okay, so again, what are the goals of this chapter? To understand the principles behind link layer services, error detection and correction. Before going to that, I want to ask you some question. We have mentioned several times that all the layers, they are working in either software or hardware. Which layers work completely on software? Can you tell me? Completely in software. Which layers work completely in software?
কিছু লেয়ার থেকে নেটওয়ার্ক লেয়ার সবগুলোই তো সফটওয়্যার।
Very good, very good. Application to network. Even network layer is completely implemented in software. So you have to keep in mind software, and then everything in communication moves as signals. So you have to convert that bits to signals. Without the hardware, you cannot do that. So the rest of the part is hardware. But data link is the only part that works both in hardware and software, right? So upper half of the data link works with the network layer for software, and the lower half of the data link works with the physical layer that is part of the hardware. So that is one thing. Another thing is data link works at the bit level, right? So that's why it is the only layer that can correct errors. Single bit error, multi-bit error. I think you have covered this in some of the courses, right? Data communication or communication theory or digital communication. We'll not cover this in this course, but we know that data link is the only layer that works in the that can correct errors because it works in the bit level. Then how data link shares a broadcast channel, that means a channel shared by multiple users, that is called multiple access. We will learn about the linked layer addressing, although we know physical layer addressing MAC already, we know that, but that is used by data link layer. And then local area networks like Ethernet is the mostly used wired LAN, and there are also virtual LANs. We will not cover virtual LAN. Virtual LAN is a mechanism where data link layer can divide the hosts in different groups. So normally we know that network layer actually creates the subnetting using IP address. Data link layer doesn't use IP address, but virtual LAN is one mechanism that can do that. Again, this will be this is covered in details in professional courses like CCN and other. Then data center will not cover, and then how this various link layer technology instantiated and implemented in the internet, we'll get an idea. So these red marked topics will only cover introduction, then multiple access protocols, then addressing, that is physical addressing and ARP switching, and then we'll cover, not cover, we'll go through an example, a day in the life of a web request. That example actually covers all the protocols and concepts that we have learned already in this course. So this is a good example to review the overall process or visualize the overall process when we browse a website. What are the protocols involved? And all the protocols we have already learned by this time. So it is probably the 6.7, the last section, and this example will give us a good knowledge about the collective scenario. Okay, let us start on data link layer introductory concepts. We call all devices as nodes. Doesn't matter it's end device or intermediate device, all are called nodes in data link layer. Why? Because again, if you go through the same diagram we have covered again and again in this course, you can see the red marked links. So even in network layer, we said the purpose of network layer is path determination or carrying a packet from one end system or host to another end system or host. This is the main purpose of network layer. So from one end system or host to another end system or host, how many links are there? Maybe 5, maybe 10, maybe 20. Doesn't matter. Host to host, but packets. That was the target of network layer. In data link layer now, we have to think about from one host to another host, there might be 5 links, might be 10 links, might be 20 links. So data link will work in each individual link. It can be wired, it can be wireless, it can be Wi-Fi, it can be cellular, it can be optical fiber, it can be UTP. So between two end system, between two hosts, there can be different type of links, but Data link layer scope is one single link always. That is transferring a frame. Data link layer packet is frame. In link layer, the PDU is frame. We have already mentioned in chapter 1. So what is the responsibility of data link layer? To transfer a packet or datagram from one node to physically adjacent node over a link. That is, a data link layer protocol will work within a single link. The link covered, the next node receives the frame, then again for the next link, that another data link layer protocol will work. Okay, so this is the idea, and this is the big difference in data link layer. Let us go through this using a real life example, and let us do it in our own way. Suppose you want to go from Dhaka to Chittagong for a visit or for some purpose. So you will start from your home at Dhaka, and you will finally reach, your target is to reach an office or a home in Chittagong. So if we think how many links, how many major links will be there, before that you have to decide how we will go there. Already we have covered this in network layer. We have to consider different factors, like expense is a factor, distance is a factor, comfort is another factor. With all these, if you just decide, for example, you decided to go through bus. With all the factors considered, you decided, okay, I will go through bus. If you go through bus, then you have to go from your house to the Dhaka bus station first, right? Then if you board on the bus will take you to the Chittagong bus station, not the final destination. And then from Chittagong bus station, you have to go to the final destination. So how many links we can grossly take here? How many links? Generally.
3 links.
Right, 3 links. From my home or house to the Dhaka bus station, from Dhaka bus station to Chittagong bus station, from Chittagong bus station to the final destination. And Dhaka bus station, Chittagong bus station, maybe your bus will take different route, but don't worry about that. Okay. Now, if you start on a particular day, start from your home, what are the possible options? You have to go to Dhaka bus station. Maybe you can call a rickshaw. Maybe you can call a CNG. Maybe you can call Uber. Maybe you can use your private transport. Anyway, but whatever you do, what will be the address? What will be the target address in this case? Is it the Chittagong address or the Dhaka bus station?
Dhaka bus station.
Right, Dhaka bus station. You will not say, okay, I want to go in this address of Chittagong. You will not say to the CNG or Uber. You will say, okay, I will go to Dhaka bus station. That is not the final destination. So that is the thing about data link layer. So my home, my house to Dhaka bus station, a data link layer protocol will work. Who is the data link layer protocol? The CNG or the rickshaw or the Uber you will call. And you will give them the address of the adjacent node. That means Dhaka bus station address. That is called the MAC address, right? If you go to Dhaka bus station, you board on the bus will take to the Chittagong bus station. Okay, fine. Again, for that bus, the destination is not the final destination. The destination is Chittagong bus station. Now, after reaching the Chittagong bus station, again you have to look for optional transport. This transport is data link layer. Maybe, for example, only rickshaw is available there. So you have only one option, rickshaw. Rickshaw is again the data link layer protocol. So there are 3 links. In each link, you have to change your transport. That is data link layer, right? So it works in a particular link. So transportation mode we call link layer protocol. Transport segment is that particular link. You are the datagram. You are the tourist, passenger. You are the datagram. And who is the travel agent? Routing algorithm. That means from whom you have brought the ticket. So this is the example we can use in our textbook. They have given the example from USA, like limousine is the car, a special car from a city, Princeton to JFK, John F. Kennedy Airport, New York. So then using the plane, there is another transport from JFK to Geneva. Geneva is a city in the Europe. and then using train from Geneva to Lausanne. So again, the same thing. From source to destination, you have to use different transport for different segments. So each transport is equivalent to the data link layer. Okay, so data link layer actually serves the network layer from transferring from one source to one destination that has multiple links, but each link contains a separate data link layer protocol. So it can be Wi-Fi, it can be Ethernet. For example, when you take connection from the ISPs, right, at your home, they give you, probably they give you wired connection up to your wireless router, right? And then from wireless router, you configure the Wi-Fi at your home. So whenever from ISP, if you think there is a wired connection, and then to your laptop or to your PC, there is a wireless connection. So this is like that. And each data link layer protocol provides different services. It may or may not provide reliability. So reliability is one service that data link layer can provide. So now let us go through what are the different services data link layer will give us. Okay, first one is called framing and link access. So what is framing? Framing means converting a packet or datagram to a frame. Frame is the PDU in data link layer. So what the source does, it receives a datagram or packet from the network layer, it adds its header and trailer and creates a frame, right? And then hands over the frame through the link to the next node. The next node receives the signals, converts to bits, converts to frames. And then if it removes the header and trailer from the frame, it will be packet or datagram handed over to the node, right? So that is the framing concept. And then link access. Link access means there can be many nodes accessing it. For example, in mobile cellular network, many of us are using mobile networks. In the same cell, in the same network, we are using mobile networks. Okay. So there are different users. They using same shared mediums. Mobile network is a different thing. And in case of wired network, we have different laptops or PCs. We are using the same wired link. So that is called link access. Now, data link layer has the responsibility to give a mechanism so that multiple users can get access in such a way each one can use the shared medium. And in case of wired LAN, there is a MAC address, you know, source MAC, destination MAC. In the frame headers, identify the source and destination. Definitely it is different from IP address. Okay, so framing and link access. The second service is reliability. But data link layer only provides reliability between adjacent nodes. Okay. Now the problem is, which layers provide reliability? Can you tell me which layers provide reliability? Is it only data link layer, or there are some other layer also provide reliability?
It is transport layer.
Right, transport layer also provide reliability. Now in data link layer, the reliability is only between adjacent nodes. That means only in a particular link. So if you have 5 links between source and destination, we don't know how many links provide reliability. It's not mandatory. That's why we still need the transport layer reliability on top. There is a question you can see, why both link level and end-to-end reliability is needed? Because link level, data link level reliability is not mandatory, not compulsory. So out of 5 links, out of 10 links, maybe some links provide reliability, some link not. But if data link provides reliability, that is better. Why? Because we don't need to go back to the source for transport layer reliability, retransmission, right? So if a data link layer provides reliability, if a packet is lost, then the immediate previous node will retransmit. We don't need to go back to the source. So that is one thing. And that's why which protocol will give reliability, which will not, it depends on low bit error links has normally doesn't give reliability, because bit error is low, so we don't need much more overhead. For example, optical fiber. Okay, for example, some other cases. But for example, in the wireless networks, there are more errors. for different reasons. Okay, so we need actually both reliability in link level and end-to-end, but data link layer also provides reliability, but remember it is not mandatory. It depends on which provides which type of link. Okay, then flow control. Again, flow control is also provided by transport layer and data link layer, but transport layer provides flow control based on the free space in the receiver's buffer. Data link layer provides flow control between the adjacent nodes. Again, if you buy a switch or hub from market, you can see in the specification, you can see 10/100 Mbps. Did you notice that? Also, when you did the lab on switch, you saw some ports has 1 Gbps, some ports has 100 Mbps speed. Did you notice? Anybody?
Yes, sir.
In that case, just think about how it can connect two devices, one with 10 Mbps, one with 100 Mbps, or how they can communicate. Because if the device with 100 Mbps transmits in 100 Mbps, 10 Mbps cannot receive. Not possible. So data link layer or switch has that responsibility. If I connect one PC with 10 Mbps in one port and another PC with 100 Mbps in another port, then internally switch will create the flow control. That means it's logical to make the 100 Mbps to 10 rather than 10 to 100. It's not possible, right? So this is called flow control, where both nodes, if they have dissimilar bit rate or transmission rate, then flow control can actually make them compatible. Okay, that is flow control. Error detection, all the layers do error detection. Similarly, data link will also do error detection. Errors can be caused by different physical phenomena like signal attenuation, noise, and receiver will detect errors. And if there is an error, it will drop the frame. And as I said, data link layer is the only layer that can also correct errors. But to correct errors, it must identify the set of bits. If a bit or set of bits is identified as error, if the bit is 0, definitely you can make it 1. If the bit is 1, make it 0. Very simple. And since data link layer is the only layer that works at bit level, it can only correct errors if possible. But no other layer can do that. So error correction is another one. And finally, there is another property I think many of you know, half duplex and full duplex. Half duplex is one-way communication. Full duplex is both-way communication. So this can be also controlled by the data link layer services. Okay, so these are the services data link layer can provide to us. Any question? Anybody? Now, where the data link layer implemented, I think I have already mentioned. There is a LAN card, network interface card. It can be built in your laptop or PC motherboard, or you can buy one from the market and you can place in your motherboard. But whatever you do, there are two parts of data link layer. One is the controller or the hardware or the circuit. Another part is the, as you said, part of the software that works with the upper layers. So data link layer that works with the CPU, communicates with the CPU, works with the upper layers. So there are two parts in the data link layer. Okay. And the next section is multiple access links. I think I will not start this today. This is the next section. So we will start this after the exam on the next Saturday. So I want to stop here. If anybody has any question, please, you can ask. Any question? Okay, no. So then please respond quickly. I am taking the attendance. Everybody please alert. Okay, Tanjina Hassan. Tanjina, are you there? Azharul Haq.
Yes, sir.
Okay, Mushfiq present. Abu Ammar.
Present ছিল স্যার।
Okay, Azizul Hakim.
Present, sir.
Okay, Mahish Shahriar,
Yes, sir.
Kamrul Hassan,
Yes, sir.
Tanvir Rahman, Ishrat Jahan,
Present, sir.
Anika Tahsin,
Yes, sir.
Shomik Ahmed,
Yes, sir.
Nuzhat present, Farhan Naj,
जी sir.
Jahara Islam, Kausar Ahmed,
Yes, sir.
Munjirul Asad,
Yes, sir.
Enamul Bari,
Present, sir.
Mohammad Shabbir,
Yes, sir.
Saima Khanum, Tawfiq Hasnain,
Present, sir.
Shihabuddin,
Present, sir.
Jannat Ara,
Yes, sir.
okay, Partho Protim,
Sarod আছে sir.
Partho, are you there? Okay, Partho, okay, present. Ifat Ahmed, Ifat,
Present, sir.
okay, Mahmud Hassan,
Present, sir.
Shahabuddin
Yes,
Sabia,
sir.
okay, Shafiqul present, Ehsanul Karim,
Yes, sir.
Shariful Islam, Saudia Haq,
Yes, sir.
Saudia, are you there?
Yes.
Saudia, okay, Noori Nawaz, Shoaib Ahmed,
Present, sir.
Shoaib Ahmed, Mehdi Hassan, Wasiul Haq,
Yes, sir.
Samiud Jaman,
Present, sir.
Samiud Jaman, okay,
Present, sir.
Adrito present, Ashikur Rahman, Sultan Ashik present, okay, Sultan Mahmud,
Yes, sir.
Sumaya Akhtar,
Present, sir.
okay, Rahul Mollik, Noyon Kanti, Sadikun Noor, Kaji Nafis,
Present, sir.
Masnad Hussain,
Present, sir.
Mia Muhammad Aziz,
Present, sir.
Faisaluddin,
Present, sir.
Nazmus Sakib,
Yes, sir.
Fahim Hassan,
Yes, sir.
Mushir Rahman,
Present, sir.
okay, Kazi Maisun,
Yes, sir.
okay. Anyone else?
Sir, Tanvir Rahman,
What's the ID?
171074.
171074. Okay, Tanvir Rahman. Anyone else?
191.
Sorry, ID
191242.
191, then 242. Rahul Mollik. Okay, anyone else?
Tanzina Hassan, serial 1.
Anyone else there? Okay, thank you very much. See you in the next class. And remember, next class we have a class test 5 that will be online. Okay. Okay, thank you very much. Allah Hafiz.
Sir.
Assalamu alaikum, sir.